Okay, so this will be about co-inductive proof systems or compositional proofs in reachability logic, and the co between parentheses there suggests that there will be both induction and co-induction, but putting induction and co-induction and all the rest would make a very long title. It's already as long. It's already long now, so let's not make it longer. Okay, so composition, the context. It's reachability logic introduced by our fellow countryman Grigore Rusu and co-authors in a series of papers, and that can be described as a language parametric logic of programs where one specifies operational semantics of programming languages and at the same time partial correctness properties of programs in the languages so defined. So partial correctness here doesn't mean that it's incomplete. It's just the technical notion of correctness on the terminated executions of a program.
Mm-hmm.
Okay, so in order to verify such statements, there is a proof system, which is sound and relatively complete. Soundness means that no invalid formulas can be proved, so that's a feature which is very desirable. And relative completeness means up to the existence of some, let's say, oracles that perform some auxiliary tasks, all valid formulas can in principle be proved. And these meta properties of the proof system are hard to prove. Unfortunately, in this setting of reachability logic, it has to be done only once. And then one can use the proof system with peace of mind, knowing that no invalid formulas will be proved. So this is in contrast to other logics of programs, such as for logic or separation logics, where there is indeed one logic per language. Okay, and then there is one proof system for each logic per language, or even for language version. And in principle, all those proof systems should be proved sound and perhaps relatively complete. And in practice, this is not done because it's too much. Okay, so the advantage of reachability logic is precisely this fact that, well, it does depend on languages, but it depends on languages as a function depends on its parameter, but the function stays the same. So this effort of soundness and relatively completeness meta properties, establishing them is done once and for all. Okay, and there are many applications, non-trivial programs from real languages that have been verified. And one observation is that, well, there are actually several versions of reachability logic, right? Not depending on languages, it's just that they were introduced and discovered in the course of time. And the proof systems there all have a co-inductive flavor. Okay, so proof systems are about proving conclusions from hypotheses, but some conclusions can migrate to hypotheses and can be used in their own proof, sometimes provided some progress has been made. So this, is indicative of the presence of co-induction. But co-induction as such, with very few exceptions, has not actually been used. So we want to push this reasoning and not only notice that there is something there, but actually use it. Okay, and we have a more practical motivation is that, well, reachability logic can prove programs which are, well, implementations or closer to implementations, but it can be interesting to verify also designs which occur earlier in, let's say, reasonable development processes than programs with known cost-effective aspects such as catching errors early, identifying key properties that could be translated and reused in program verifications. So it makes sense to verify designs before programs, not instead of verifying programs, just like program verification does not replace final system testing, right? But all these can help in obtaining good quality software in the end. And as designs, we will use transition systems, which are perhaps the simplest possible model. So yeah, for us, a transition system is just a set of states and the binary relation called the transition relation. And here we have an example in blue. Okay, so this is the real definition of the transition system, S and arrow, but a more, let's say, friendly representation is the graphical one. So this is a finite state machine extended with variables, an extended finite state machine. So it has 3 control nodes, L0, L1, and 2, and 3 arrows between the nodes. And the arrows are decorated sometimes with guards, like this one, or, whoops, or that one. Yeah, the guards put conditions on the firing on the transitions, and when firing a transition, a set of parallel assignments can be performed. So again, this is just a graphical representation. There is an underlying transition system with the formal definition in blue here. And well, I'm not going to read the details. It's just that the set of states is a location and values for the 3 variables, natural numbers. And the transition relation is the union of 3 big transition relations that are denoted by the arrows there. And let's just notice that M there is not modified anywhere. It's like a symbolic constant. And the goal of this machine is to compute the sum of the first M natural numbers. Okay, so this work will be about reachability logic on transition systems. So reachability logic has been shown to be very versatile to represent the semantics of a large variety of different kinds of programming languages, and it has been also extended to more general things like rewriting theories. So let's see whether this works well for transition systems. Okay, so we do that. And we are going to propose 3 proof systems that use co-induction and induction in various proportions. We're going to establish their soundness and completeness in proof assistance. So I'm not going to present the source code of the Koch and Isabelle Hall formalizations. This is just a description of the work, of which I'm going to show some fragments here. Okay, and so for scalability, we focus on compositionality, which can be broadly described as prove local properties on subsystems called, well, components, and reuse those as lemmas in proofs of more global properties on bigger systems. Okay. So this is, of course, key for scalability if these proof systems are going to scale up. And there is a positive correlation between the amount of induction that a proof system has, the degree of which the co-induction is specific to our problem, proving reachability logic formulas, the amount of compositionality, and the hardness of the soundness proof. Okay. So this is not a general observation. It's just that it turns out that for our 3 proof systems, there's a positive correlation between these 4 aspects. So there is a winner in the proof system, among the proof systems, the most compositional one, because it will be the most scalable one. But I think that the others also are worth presenting because they show some interesting features. And I hope to share with you my interest for them. Okay, so after this introduction, some preliminaries on induction and co-induction, transition systems and reachability logic on transition systems. Then the 3 proof systems in order of complexity. A few words about their implementation in Isabelle Hall and Koch, 2 proof assistants that have 2 rather different support levels for co-induction, and then conclusion and future work. So, preliminaries now. Induction and co-induction in one slide. Let's assume a complete lattice. So there's a set L. There's an order relation. There's a least upper bound, a greatest lower bound, the top and the bottom. So I'm going often to use inclusion for the order, union for the least upper bound, intersection for the greatest lower bound because they look like that. Okay, and let's assume a monotone function with respect to the order on the set, on the set of the lattice. So a fixed point of a function is element x such that f of x equals x, and in this setting, f has both smallest fixed point and the greatest fixed point with respect to the order again. So the smallest is denoted by mu, and the greatest is denoted by nu. And then we have the so-called co-induction principles. There's the weak or regular one, which says that a set is included in the greatest fixed point of this function if it is, well, included in the image of itself by the function. Okay. And there's the strong version. So I'm going to try to point without clicking. The strong version is actually if and only if. And one is allowed to add as inclusion the greatest fixed point in the argument of the function. So most of the times we just use the regular one, and sometimes, actually only once, we use the strong one or mention it in this presentation. And of course, there is the induction principle, the regular one, and there's a strong one too. So now it's about the smallest fixed point, and the inclusions or the orders are inversed. And moreover, once in the presentation, we mentioned the fact that if is continuous, so it distributes over infinite disjunction, then the smallest fixed point exists, and it is the infinite union of, well, starting with bottom and iterating the function f and taking the infinite unit of all these iterations.
No.
So, yes?
No, it's okay, it's fine. Well, just on observation, you have a variant for the greatest fixed point. F is co-continuous that distributes over joint.
Sure.
Okay, you can mention that, I guess, on the slide.
Yes, I think I will just mention that there is one, like there is a strong version of the induction principle too, but I'm not going to mention it in the presentation. So
Yeah,
these are the only things I'm going to mention.
Okay.
So it's yeah. I'm trying to reduce the amount of stuff on slides.
Okay.
Right. So example, the natural numbers, inductively and co-inductively. So let's assume, for the sake of the presentation, that there is a universal set of all the elements of discourse. I know that this is a controversial issue, but let's just assume that we have one, and there is a constant symbol 0 there, and a postfix unary function called +1. Okay, so postfix means that it's applied after the argument, so we have things like x +1. That would be called a successor sometimes. Okay. And let's not interpret things too much. Let's not interpret 0, plus, and 1 for the moment. It's just syntax. Okay. So the natural numbers can be described or defined as the smallest fixed point of this functional here between the subsets of U and the subsets of U that do the following things. So to a set, it associates the set 0 union the set of, well, +1 applied to the elements of X. Right, so one can see that if we remember the thing that the smallest fixed point is the union of iterations starting from bottom. Okay, so here we obtain in this way the set 0, then the set 0 plus 1, then the set 0 plus 1 plus 1, etc. So we eventually end up with an image of the natural numbers. So but there's a greatest fixed point to this function too, and it turns out that it is well, the natural numbers plus one element, let's call it infinity, and infinity has this property that infinity plus 1 equals infinity. Okay, so yeah, by just taking the greatest fixed point, we obtain a Reachability set with this particular element that we can interpret, let's say, intuitively as being the smallest infinity possible. Okay, so we're going to use transition systems, and let's define a few things about them, co-inductively, again, as an example, but also to introduce the matter. So, yeah, transition systems are just a set of states and a binary relation. We're going to use the notion of final states, denoted by the black hole. Yeah, it's the set of states from which nothing exists, nothing exits, no transition exits. And we're going to be interested in executions or paths of transition systems that are non-empty and possibly infinite. So those would be the greatest fixed point of a function that to a set of elements associates, so the set of states that are final, so these are paths, and the set of concatenations of a state and a path, well, an element in X, such that there is a transition between the state and the head of the path that we're building, with the assumed definition that well, we had a function on the set we're currently defining. This is allowed in some proof assistance. Yeah, so that's the head is always the first element, essentially. Okay, so yeah, formally this can be defined in this manner, and well, all the time there is a function and greatest fixed point if we're going to talk about co-induction. But I'm not going to show the function all the time. Like, for example, here, well, we want just to define the length of paths. So that is a natural number and possibly infinity. And it's defined equationally with a co-recursive call. Actually, yeah, there is a function and the greatest fixed points there, but I'm not going to show that. So, the proof system is a kind of symbolic manipulation of well, formulas. So we're going to use a symbolic representation of sets of states as well, state predicates. So given a transition system, the set of state predicates that sometimes possibly I'm going to call symbolic states because it's symbolic representation. Well, it's a set of functions from the set of states to the booleans, and we just write P of S instead of P of S equals true. Okay, so this set of functions is organized as a complete lattice with the order, the least upper bound, the greater lower bound, top and bottom defined in this way. And just as we raised states to a symbolic representation state predicates, we're going to need to raise the transition relation on something called the symbolic transition function that operates on state predicates. It has this definition, but perhaps a figure tells more things in an easy way. So if P is satisfied by the set of states in this ovoid here, then delta P, the symbolic transition function applied to P, is the set of states, or is satisfied by the states that are successors by one step of the transition relation of states satisfying P. So that's the intuitive meaning of the definition there, which had an existential quantifier. Okay, so now we can introduce reachability logic. So yeah, on transition systems, so syntactically, it's very simple. It's a pair of symbolic states. And the constructor of the pair is this symbol arrow diamond called leads to, okay, or reaches. And the intuitive meaning is that, well, yeah, from P, inevitably, in some sense, one will reach Q. So this inevitably, this operator is borrowed from linear temporal logic, and actually, well, yeah, reachability formulas are the corresponding linear temporal logic formulas interpreted on finite paths. So this is syntax. Now for semantics, I'm going to need to introduce a relation. Actually, that's the greatest fixed point of a function. It's the greatest relation between paths and symbolic states, defined as follows. So either the path is just one state, and then the symbolic state R needs to hold there, or it's a concatenation of states and another path, and the symbolic state R needs to hold on S, or we postpone. Yeah, so it's still a concatenation of a state and a path tau prime there, but now we postpone. Tau prime has to reach, well, to satisfy, to be in this curly arrow relation, sorry, with respect to R. Right, so, well, we take the greatest fixed point on that, and then the validity of L goes to R is defined as, well, for all paths, of course, in the underlying transition system, if they start from the left-hand side, they reach, in the sense of this curly arrow, the right-hand side. So again, a figure is better. We have L, we have R, so this is the reachability formula. L goes to R. And for this formula to be valid, we just look at the paths that start in the left-hand side. So they will be denoted with the, well, they just start with inside, right? And so we look at the paths first that are, terminated, meaning that they end up in a black hole, no transition X is there. So all these paths that start in L that are terminated need to encounter R at some point, either at the end or in the middle, or perhaps even the beginning, but somewhere they have to meet a state satisfying R. Whereas an infinite path like this one is not constrained by validity, right? So validity of reachability logic formulas is really about partial correctness. Termination is not an element of this question. So example.
Sorry, Vlad. For the last line that you have in there, maybe you should point out that it has to go through R. Just put an intersection point, because I see this picture as a 3D picture, and.
So I'm trying not to point actually too much on the screen because it's going to jump ahead. So in real life, I will have a pointer.
Okay.
Actually, I bought a pointer of my own, so I'm sure that I'm familiar with it because there are so many models. So I will point to things on the screen. Here I'm trying not to use the mouse too much because it's sensitive also.
Okay.
Sorry about that. Okay, so examples of formulas still on this state machine and the underlying transition system. Essentially, this formula says that the state machine, the underlying transition system, satisfies its expected functional correctness property, that it computes the sum of the first m natural numbers. More precisely, if we start in the leftmost location, on all terminating executions, we end up in the location L2 with S containing the sum of the first m natural numbers. Okay, so it's really on terminated executions, because if I change the machine a little bit, so I remove this guard and I strengthen it here. So now there is an infinite loop. Okay, so there's an infinite path. But the formula still holds because those infinite paths don't really matter. Okay, so the machine used to be deterministic, now it's non-deterministic, the underlying transition system too, and the formula still holds. Okay, so one other formula that I would like to show, its meaning is not essential, it's just that, well, it's colored red, and this suggests that it is about the submachine and the underlying sum transition system, also colored red here. And it's true, and it turns out that one can establish the validity of this red formula just on the red submachine sub-transition system, and deduce that it holds on the whole machine and whole transition system. So, well, how does this work? So validity is, in some sense, compositional in a structural sense. So we say that a transition system with primed things, state and transition relation, is a component of another one with unprimed elements. If it is a sub-transition system, so the state sets and the transition relation as set, the primes are included in the non-primes. There is a notion of full subrelation. Okay, this means that the smallest relation on its set of states, the smaller set of states, contains all the transitions. So there's no contribution by the greater relation. Or said differently, the greater relation restricted to the smaller set is included in the smaller relation. And a notion of clean border, it says that if we exit the component, the states of the component, by a transition which is necessarily one of the bigger system, then we can only exit via a final state in the sense of the smaller transition system. Okay, so this means that if we exit, we cannot go back. It's a notion of clean border. And in particular, this is satisfied for deterministic relations. Okay, so when we have a component like this, we use this left slice symbol. And again, well, in terms of underlying transition systems, the underlying transition system in red is a component in the sense of the whole underlying transition system for the whole machine. Okay, so it's deterministic. The clean border is implied. Sorry about that. No, not a good idea to point. And whoa, okay. And well, you see that there are no black arrows on the red location. Okay, so yeah, the red transitions are all there are on the red location. So we have a full subtransition system. Okay, so why is this important? Well, because one can establish the validity of a formula on a component, and if it is indeed a component of a large transition system, then it also the formula is also valid on the whole transition system, as this red formula. It is valid on the component, and it is hence valid on the whole transition system. So this was not preliminaries anymore. It's already a result, which, as far as I know, is new. So, well, we have a notion of validity, but yeah, except in the simplest logics, one does not use the semantical definitions directly for proving formulas. One goes through proof systems that mechanically manipulate formulas, and of course there should be well, the soundness and hopefully completeness results connecting the syntax and the semantics. Okay, so the three proof systems in order of let's say complexity, and we start with the first one. This one is so simple that it admits a graphical illustration. Okay, so we have our formula L goes to R. And in general, there is a non-empty intersection between L and R. So what the first proof system does is it repeats the following things. It takes an over-approximation of the difference between L and R, and it makes a symbolic step. And then it takes an over-approximation of the new difference, and it takes a symbolic step, and so on and so forth, forever. So intuitively, this is this shows all the ways in which L might eventually go to R. Okay, so slightly more formally as an inference rule. Okay, so we have rule, it's going to be called step. And it says the following thing: in order to prove L goes to R, you can prove another formula, symbolic transition function applied to some L prime goes to R, and L prime is an over approximation of the difference between L and R, which can be written also like this. And there should be no black holes in L prime, right? Because if there is a black hole there, so no transition is possible, and we haven't reached R yet, then we'll probably never reach it. This is the motivation of this second condition. Okay, so this is applied forever. So this new suggests that there's an infinity going on here. Always postpone, always prove another formula. Right, so, well, this is slightly more formal, but not quite yet. Mathematically, if we want to define that, so we need to define a function on sets of formulas, and this function just describes what the proof system does when applied top to bottom, actually, to a set of formulas. What are the set of formulas that it can produce? Okay, so F is monotone, and then we can define this proof system. So it's the simple bar proof system, like that. So T proves phi if phi is in the greatest fixed point of this function. So this is the mathematical definition of the proof system. Okay, so, well, we hope to prove only valid formulas, and it's indeed the case. So I'm going to state the lemmas and just say the key idea for the proof, because, of course, there's no time to show all the detail, right? So you've seen the relation, curly arrow, between paths and symbolic states. So since it was defined co-inductively, it has an associated co-induction principle, which is just an instance of Tarski's co-induction principle when applied to this capital F, if you remember, which is the function involved here, of which this curly arrow is the greatest fixed point. Okay. So if it is spelled out in all details, this is what the co-induction principle for this relation says. And it's about showing that a certain relation R is a subset of this curly arrow relation. Right. So, well, I'm not going to read all the details, but this is the general idea. We just instantiate Tarski's co-induction principle, and then in order to prove soundness, so deduction implies validity, we just have to instantiate this R in the lemma with the appropriate instance so that, well, the conditions there hold. And it turns out that this R is the appropriate one. Okay. So in general proofs by co-induction, there is a co-induction principle, there is a parameter there, which is in general, yeah, an imaginary predicate, let's say, and it has to be given a value, and this is where creativity of the user is involved.
Mm-hmm.
So, right, but we only prove valid formula. This is fine, but what formulas do we prove? How do we prove formulas? So this is now the co-induction principle for the proof system, which is also a consequence of Tarski's, and it said, okay, if you want to prove phi in the transistor system T, come up with a set of formulas that contain our formula, and which the set must be closed in some sense. If we remember the proof system expressed as an inference rule, then it has to be closed by application of the inference rule in some sense, but bottom to top. Okay, so there's obviously a relation between this co-induction principle and the proof system, even expressed as an inference rule. So yeah, this to replace the reading of this complicated statement. Okay, so what can we prove with this co-induction principle? Well, there is a nice class of formulas that can prove. Okay, so we prove any formula L goes to R if we can come up with a Q called a quasi-invariant, because it behaves like an invariant but not quite. That satisfies these three inclusions in particular. So the post-image of Q is included in Q, but not only Q. It can also diverge to R. So if it was just Q, it would be an invariant, but it's not. So it's a quasi-invariant. The same with respect to the initial states, if we look at L as initial states. Okay, so if we can come up with a Q like that, then we can actually build a proof. And to do that, well, again, it's a matter of using the co-induction principle with the appropriate instance of the predicate there, or set of formulas, which is the same. So in particular, this one works. Okay. So actually, this is useful because it reduces the proof of reachability to invariance in some sense, and in a case study to illustrate the fact that this can scale up. To some extent, we've verified the design of a security hypervisor, just as a matter of illustrating this on a non-trivial example, but let's see it on a trivial example. So, well, this, again, formula, we want to prove it on the red submachine, and it turns out that by choosing Q in this way, well, it will work. The three implications in the lemma will hold. And it's indeed a quasi-invariant because at location R1, it's like an invariant. It's almost an invariant. If it was an invariant, here it would be a non-strict inequality. So yeah, if we can come up with such a Q, then we won. And it turns out that for valid formulas, we can always come up with such a Q, this one. Right? So yeah, this Q, if the formula is valid, will satisfy the three implications or inclusions of the lemma, and then we have completeness. Yeah. So any valid formula is provable. Okay. So now question to Radio Erevan. I'm assuming that in the room the reference to Radio Erevan is known. So okay, we don't know whether phi is valid, but we have this soundness result. Okay, so if we manage to prove it, it will be valid. And we have this particular Q, sorry about that. So why don't we always try this one? Yeah. Because if the formula turns out to be valid, it will work. Right? So we can prove any formula. The answer is yes and no. So one can use this Q. But if you do that, well, notice that the Q here is very expressive. It has things about semantics. So this just amounts to proving validity directly from semantical definitions. So one loses every benefit of having a proof system. So it's not such a good idea to use this Q. But other Qs, like the one shown in the previous slide, yeah, introduced by the user, can work. Okay, so yeah, this is its completeness, but using very expressive predicates that won't work in practice. Okay, so if we say that, we are pretty sure that we're not saying false things. Okay, so how about compositionality? So structural compositionality works because we have an equivalence between provability and validity, and we had that for validity, so this works. How about logical compositionality? So this is just the following thing. I want to prove phi. Well, I would like to be able to prove a lemma phi prime and then to use phi prime in the proof of phi. That's a reasonable requirement. The problem is that this simple proof system does not even admit syntactic hypotheses. I cannot write that. So if I'm going to have some kind of compositionality in this logical sense, I must add hypotheses, and to handle them. But if I add hypotheses, the new rule will not be co-inductive. The proof system will be mixed because this rule will only be applicable a finite number of times, actually at most once on finite proofs. Okay, so it changes the nature of the proof system. It's not purely co-inductive as it is now. And since I'm going to add hypotheses and an inductive rule to manage them, let's also split this step rule, which did many things, into several rules. And this is the second proof system, denoted with a double bar here. Okay, so let's go through the rules very briefly. The hypothesis rule says that, well, we now have hypotheses, so if a formula is among the hypotheses, it's proved. The trivial rule says that, well, R goes to R. Well, it's already there, it doesn't need to go. The strengthening rule says that, well, you can always prove a stronger formula by taking a bigger left-hand side, because this places a strong requirement on more paths that start from the left-hand side. The split rule says that, when one applies this proof system, the left-hand side can grow because there are there are two different arrows in a symbolic representation of transition system that would create a disjunction. So in order to limit this growth, we split this into two formulas to prove. This transitivity rule, it's also a sort of divide and conquer. So we want to prove L goes to R. Well, if we can come up with an M such that L goes to M and M goes to R, then we have proved L goes to R. But notice that this rule is not so nice because it mixes syntax and semantics. So yeah, syntax is the proof system, semantics is validity. Please bear with me, I've tried with two different proof assistants, having two different notions of co-induction, to get rid of this, and I never managed. So it's always inevitably somehow the rule is imperfect. I need validity here. I cannot have provability. Okay, and there's the step rule, which is now not only referring to an L, not an L prime. Yeah, so this is again co-inductive. The L prime, if I wanted it, I would use the other rules. Okay, so this is definitely needs to be applied an infinite number of times, but the other rules should not be applied an infinite number of times. If I'm going to allow this, then it would be unsound, because any formula could be proved by just reducing with this rule, for example, the proof of a formula to itself, and so on and so forth forever. So this rule is co-inductive. The other ones are not. More precisely, what I want is a proof system that does the following thing. At the beginning, it can apply the first 5 rules for simplification purposes until the first application of the step. And then again, finitely many times the first 5 rules until there is another application of step, and then and again. So like phases that can contain a finite number of applications of the first 5 rules, followed by an application of the step rule. Okay. So this is what I want in words. But if I'm going to describe this mathematically, well, I have to do that. So please bear with me. So this function here is the effect of applying the proof system.
Oh, that's the
Sorry about that, of applying the proof system to a set of states. So yeah, it's just an encoding of the proof system, right? So we have a set of formulas, and these are the formulas that it can generate. So this function is monotone, and it's actually continuous. So it has a least fixed point, which is this infinite union. It has an induction principle, but now there is still a y here in the as an underscore. So the mapping of y to this expression depending on y, and that already has a smallest fixed point. It's also monotone, and it has greatest fixed point. So now I have a greatest fixed point and smallest fixed point. And then the proof system is defined as follows. So T and hypothesis H deduce phi if phi is this greater than smallest fixed point. So it's clearly mixed inductive and co-inductive. And it has a co-induction principle saying when a formula is proved. So both the induction and the co-induction principle are instances of those of Tarski.
Mm-hmm.
Okay, so it's a clearly mixed proof system.
Mm-hmm.
Soundness and completeness. So soundness now, since there are hypotheses, it is the following as follows. So if all the hypotheses are valid, then proving phi under the hypotheses implies that phi is also valid. And of course, I cannot give the details of the proof. It's a bit more involved. It uses both the induction principle shown before and the co-induction principle for a variant of this curly arrow relation that occurs in validity. So it's a bit involved. This is so annoying. Okay, so soundness is a bit more involved. There is the same lemma of reduction of reachability to quasi-invariance. The proof is different, but it's still there. So the proof, well, uses some of the elements that I've listed on the previous slide. I cannot really go into details. Most of these things have been checked in proof assistance, so they work. And then we get the same completeness result as before. Okay, so regarding compositionality, now we have some of it. So there was this. Yeah.
You can continue, Vlad.
Okay, so we had this logical compositionality that was asymmetric, and we can combine it with the structural compositionality in this theorem, saying that okay, if C is a component of T, and on C you prove phi prime, and on T using phi prime you prove phi, then you've just proved phi. Okay. And the second proof here can be actually weakened to bring phi prime of just phi, sorry, on a component. It can be C, it can be another component prime, but notice that the phi should talk about the states of the component. It's always like that. Yeah, it talks about the states of the proof system of the transition system that is well in the before the V dash system. So we have some compositionality. So yeah, summing up, it's mixed inductive and co-inductive. the amount of induction has grown. Of course, there was none. The co-induction has become more specialized because where there was just one rule that was doing everything, and that was inductive, that was, sorry, co-inductive. Now there is one special rule step, which is co-inductive, and the other ones are just there for simplification purposes. The soundness proof is more involved, compositionality is better, but there's still this issue of the transitivity rule that mixes syntax and semantics. So this is not elegant, but not only that, it has practical purposes. Sometimes it's just, sometimes compositionality cannot be applied because of this problem of the transitivity rule. So this needs to be fixed. So, well, this is fixed in the third proof system with the 3 bars. Now there are 9 rules. And please notice that now one operates with tagged formulas. Formulas are tagged with a Boolean. So if you look at the heap rule, well, we can prove a formula if it is in the hypothesis, but only if it is tagged with true. True is green. There are the other rules that we've already seen that just pass around the Boolean. So if it's a cyan B, then it could be true or false, any of those. And notice that transitivity now is clean, so it's only about syntax. There's the step rule, which was special before, but now it's even more special. It is the one that enables progress in our proof system, and progress enables the applicability of co-inductive hypotheses. So these hypotheses here are now co-inductive hypotheses. Okay, and it's not a constant set as before. It can be enriched. So, for example, we have this specialized cut rule, which says that if you want to prove phi tagged with some B, then you can prove phi tagged with some B, provided that, well, you have in the hypothesis phi prime, but you need to prove phi prime starting from the bottom, so tagged with false. There's this Koff rule that it's essentially the same, but it's for, yeah, it's for the same phi equals phi prime, but we shouldn't have 2 trees there. So it says, okay, we want to prove phi. Let's prove it starting from the bottom, from false, and we're allowed to assume it. Okay. So this is called Koff in reference to a tactic in Coq that does exactly that. It copies the goal into hypothesis, and it allows only the using of the hypothesis later, like here. Okay. So if we didn't have this constraint that the formula is tagged with true, then we could prove any formula just by assuming it and then proving it with heap. Okay. So the tags are really there to enforce soundness. And there is this clear rule that, well, if we read it from bottom to top, it enables us to delete the hypothesis. Okay, so now we have a proof system with even more induction. All the rules are inductive. Yeah, no more infinite proofs, no more co-induction principles. There is co-induction, but it is encoded in the proof system itself, and it's very specific to our problem because, well, it says that this is the way to make progress. So, well, the soundness and completeness are complicated, right? So it's now not a co-induction and not a simple induction thing. It's a well-founded induction on a lexicographic product on a certain set. It's very domain specific. So, well, details can be found in a paper, but well, I'm not going to go into them here. What do we gain with this, let's say, most domain-specific proof system? Well, a nice compositionality, combining structure and symmetrical logical compositionality. So if we have 2 components, C1 and C2 of a transition system T, and on each component we prove one formula by assuming another one, then both formulas are proved in the whole proof system. And this generalizes to more than 2, and it works for mutually dependent loops in transition systems, or if these were languages, for mutually recursive functions. Right, so a few words about implementations of those in Isabelle Hall and Coq. Actually, we started with Coq, and there were some difficulties there, so we asked Isabelle Hall for a second opinion. So let's present the Isabelle Hall thing first. It's really Knaster-Tarski induction and co-induction all the way, with some syntactical sugar to hide the fact that there are functions and fixed points there. and it's quite automated. In particular, it automatically generates and proves induction and co-induction principles. And there's commands called induction, respectively co-induction, for partially automatic, let's say automated instantiation of those parameters occurring in the induction and co-induction principles, right? Generally speaking, it's very automated and nice to use. And we formalized the first two proof systems. They are not the third one for the moment. Now, in Coq, it's quite different. Coq is based on the Curry-Howard isomorphism, which in particular says that inductive proofs are recursive programs, co-inductive proofs are co-recursive programs, and in particular for the co-recursive programs, there is a well-formedness condition that is quite complex in theory and especially in practice. One ends up with problems and error messages that are hard to understand. But, well, in order to perform proof by co-induction, there is a tactic called cofix that copies conclusions in hypotheses, like in the rule that I've shown before. And that can be only, well, the new hypothesis can only be used when some progress has been made. But, well, there are difficulties because the well-formedness condition is not really clear in the implementation. So we managed to prove the first proof system with using cofix. The second one, cofix broke down because somehow it doesn't like to be mixed with induction. But there is, fortunately, a package called Paco and a replacement command called pcofix that settled the problem. And the third proof system, it's completely different, the proof. It's by well-founded induction. And there, it was nice to have a rich type system in Coq with dependent types that doesn't exist in Isabelle. So there are advantages and disadvantages. Okay, so, well, to conclude, I've shown three proof systems for reachability logic on transition systems, all sound and complete. The first one is simple, purely co-inductive, and it has only a weak notion of compositionality. The second one is medium complexity. It's a mixture of induction and co-induction. Co-induction becomes more focused to one rule, and it has better compositionality. And the third one, well, it's the most complex. It's purely inductive, but with a domain-specific co-induction encoded inside, and it has the best compositionality. So I declare the third one to be the winner. And as future work, some proofs need to be finished and polished. We have a large base of monadic imperative code in the team, which can be seen as a shallow embedding of an imperative language in Coq, and we'd like to apply this third proof system to that in order to show that it also works for languages. Of course, languages that have an operation semantics defining a transition system in the end. We've started, and we would like to do some more transfer of the better support, in my opinion, of Isabelle whole co-induction into Coq. And, well, all the compositionality we've seen is structural and logical, but there is a traditional notion of compositionality with respect to parallelism. So assume guarantee operations that are also co-inductive. So this could be interesting to incorporate in future versions of the proof system. Mm-hmm. That was the end of the presentation. Thank you for listening.
Okay.